Hello, my name is Sarah Foss, and today I'll be presenting the paper Event Representations for Automated Story Generation with Deep Neural Nets by Lara J. Martin and others. Humans have been telling stories for thousands of years, sharing them orally even before the invention of writing. Stories are built with recognizable structures and patterns, and in those patterns we find meaning. We use stories to make sense of our world and to share that understanding with others. Storytelling plays an important role in both education and entertainment. Because stories are made up of patterns, stories seem like a natural fit for artificial intelligence research. In fact, since the 1970s, researchers have been automating story generation with artificial intelligence. Two of the most common systems used even today are symbolic planning and case-based reasoning, both of which can produce relatively robust stories. The major problem is that with both of the methods, they require a user to enter input for the story generation, meaning they are not actually fully automated. Open story generation, on the other hand, is an automated process that generates a story with the use of machine learning rather than relying on a priori knowledge provided by the user. The authors of this paper explore the use of recurrent encoder-decoder neural networks for open story generation. In their system, they utilize two neural networks, event-to-event and event-to-sentence, and both of these networks work together to produce the story. The first step is that a sentence is translated into an event format, then given as an input to the event-to-event network, which then predicts the following sentence. Then, the predicted sentence is translated by the event-to-sentence back into English language. To continue story generation, that predicted event can be fed back into the event-to-event network. Before we get into all the details of the event-to-event and event-to-sentence networks, I would like to introduce some background information on neural networks. This is a representation of a basic feed-forward perceptron neural network, which is a model used for machine learning. In this simple example, it has 3 layers, although a neural network may have many more layers. As you can see, each node, or neuron, is interconnected by many other neurons. Each of the incoming connections to a neuron will be assigned a weight. When a neuron receives an incoming data item through its connection, it will multiply the data by the associated weight and add the node's bias. It will then get passed to the neuron's activation function, which will determine whether or not the data will be propagated or passed forward. If it is propagated, it will be passed to the output layer and a prediction will be made. During training, the output predictions are compared to the ground truth or correct answer, and that information is sent back through the network, and the weights are adjusted accordingly. This is known as backpropagation. This is how the neural network model learns. This is very handy, but what if we wanted to pass a sequence of data into our neural network, like a sentence, perhaps to predict what language it is written in? Can it keep track of the previous word that was entered as input? That is tricky for a basic feed-forward network, but a recurrent neural network can handle that. A recurrent neural network is a neural network with a loop. The loop allows information to be saved as a hidden state and be passed along to the next step of the network. If you unroll the recurrent neural network, you can see that the model resembles a chain, and that with each iteration of the model, that hidden state is being passed along to the next successive hidden layer for calculation. However, there is still a problem. Because standard recurrent neural networks generally have relatively simple structures, it becomes difficult to keep large amounts of data in their memories. See, this is where long short-term memory, or LSTM, networks come in. LSTMs have a similar chain-like structure to a standard RNN, but instead of one neural network layer in a cell, they have 4. These 4 layers allow LSTMs to keep a longer memory. Along with an activation function layer, LSTMs have 3 gates that allow the cell to add or remove information to the hidden cell state that gets passed along to the next LSTM cell. The first gate is called the forget gate layer. This gate allows the hidden cell memory to either keep or forget any or all of the data it's currently holding. Next is the input gate layer. This gate determines whether the hidden cell state should be updated with the new input information. Finally, there is the output gate, which will decide what part of the hidden cell state to input. Now, we have one more neural network model to look at. With open story generation, we want to be able to feed an entire event into a network before we generate the next event. An LSTM model on its own is good because it has a long memory, but it generates an output with every input. Enter the sequence-to-sequence model. The neural network used in this research was based on an encoder-decoder recurrent neural network, or the sequence-to-sequence model, which is a deep learning network that is trained to take a sequence as input and output a predicted sequence. The model uses two LSTM networks, one for encoding the entire input sequence into a single vector, and one for decoding the vector and outputting the next sequence. So you can see here that we are passing the phrase learning coding one token at a time into the encoder LSTM, which then gets stored as a single encoded vector. And then we pass the last character of our phrase into the decoder LSTM, which is just the end of sentence token. And from there, we begin to output the next phrase, one token at a time. Now that we have covered the neural network, we will begin to look at the pieces of event-to-event and event-to-sentence systems. The researchers used a corpus of movie plot summaries extracted from Wikipedia as a dataset to train and test their models. This ensured that their stories would be generated from a large and varied domain. Movie plot summaries also tend to have clear and concise event descriptions, as you can see here in this Goblet of Fire plot, which you will soon see is very important. Now, I would like to define what an event is in the context of story generation. An event is a unit of story that contains a world state change. A world state change means that something took some sort of action to change the state. So at minimum, you need a verb and a subject. However, a well-formed event would generally have more descriptive information in it, such as an object of the verb. It is important to have as many well-formed events as possible, because well-constructed events, if they are represented correctly, can help the model achieve coherent story generation, which is one of the main story generation goals. Another thing to keep in mind is that event representations must be descriptive enough to preserve the semantic meaning of the event, but also be generic enough to increase potential overlap of events across stories. The researchers produced the probability distribution for their model with an encoder-decoder recurrent neural network with the following parameters. As an increased level of abstraction for the parameters could positively affect the predicted output, all words were stemmed and they developed a 4-tuple representation for events, where S is the subject of the verb, V is the verb, O is the object of the verb, and M is the modifier. Now, the modifier could be a couple of different things. It could be a propositional object. So the store is around the corner. So the propositional object there is corner. An indirect object, I wrote her a letter. In that case, her is the indirect object. A causal complement, I was glad that he drove. Drove is a causal complement. Now, any other dependency that cannot be identified is a modifier. So if it can't be identified, the placeholder, the empty set, or empty parameters is inserted. So you can see here, so in just a basic event representation, we would have, say, the sentence, John went to the store. It would be represented as John, go, store, empty. The event translation process could also optionally extract multiple events per sentence. So if we have the sentence, John and Mary went to the store, it would be represented as John, go, store, empty, and also another one, Mary, go, store, empty. Beyond the simple subject, verb, object, and modifier event representation, they developed the following variations. So generalized. So in this case, we're really generalizing everything as much as we possibly can. So named entities were identified and replaced with their name entity recognition, or NER category. So for example, we have location, organization, etc. All right. And so if someone was going somewhere, if they're saying they're going to the store, then store would be replaced by location. Now, person names, so if it was identified as a person, it would be replaced with the characters CHAR, so char, with a number at the end, so N, where N represents the nth character name in the sentence.
the N is reset every sentence. The other nouns were replaced by a more generalized synonym using the lexical database WordNet. So if there was, say, a car, it would be replaced with self-propelled vehicle, N01. So in that case, N stands for the fact that it's a noun, and then the O1 stands for it's the first description of a self-propelled vehicle there. And then the verbs were replaced by VerbNet. So for example, if we had arriving or arrived, it would be replaced by a more general escape. So looking down at the bottom, we can see a generalized version of John went to the store. So we would see char 1, escape, location, and empty. So another variation we had was character name numbering. So rather than resetting N with that char every sentence, the N was reset after every input-output pair. So it stayed the same over 2 sentences. So for example, we have John went to the store with Susan. Susan bought milk. So we have char 1, escape, location, and then we've got char 2, so that's Susan. And then we have char 2, so Susan is staying the same over both sentences there. Get, beverage, empty. So that's just keeping that character name numbering.
And finally, we have adding genre information. So they used topic modeling with some Python, and they classified each event into a genre and added the genre to each event representation, creating a 5-tuple with subject, verb, object, modifier, and genre. So that way it would look like John went to the store, we have char, escape, location, empty, and then we have a genre number at the end there. Now that we've talked about the event representation format, let's talk about the first network, the event-to-event network. As mentioned previously, this network is a sequence-to-sequence model used to predict the next event sequence given an event. This model takes a formatted event representation as its input, so subject, verb, object, and modifier in that order, and outputs an event representation in the same format. As there were a number of probabilities for each token when generating the output, they needed some sort of tie-breaking algorithm. So they used a greedy algorithm to produce the final sequence by taking the token with the highest probability at each step. Now, the first set of experiments that the researchers conducted sought to see how different event representation formats affected the predictions of the event-to-event network. So they evaluated their results using 2 metrics. The first one here is perplexity. So that's the measure of how well the trained probabilistic model can predict the data. For the perplexity measurements, the larger the unigram perplexity, the less likely a model is to produce the next unigram in a test data set. So here we are looking for the smallest perplexity numbers. Smaller means better in this case. The next metric we're going to look at is the BLUE score. So this is the measure of the similarity between a generated sentence and a true sentence. The BLUE score, which stands for Bilingual Evaluation Understudy, uses a modified precision metric to measure similarity. Like a traditional precision score, it measures how many of the same words appears in a generated candidate sentence and the true reference sentences. So the candidate sentences are generated and the reference sentences are true. So, however, one of the things is using single words they don't really produce human readable sentences well. So the BLUE score uses n-grams or n contiguous sequences of tokens from a sentence. Longer n-grams tend to produce more fluent sentences. So let's start by looking at a traditional precision score. It's pretty easy to calculate. We just need to count how many n-grams there are in a candidate sentence. In this case, if we are looking at unigrams, so each word separately, there are 7. So each word separately, the cat, the cat, the cat, the. And if we are looking at bigrams, which are 2 word groups, then there are 6. So the cat the cat, the cat, cat the. Now, in order to calculate the precision score, we need to count how many of the candidate n-grams appear in the reference sentences. So for the unigrams, all of the unigrams are actually found in the reference sentences. So we can see here the cat, the cat, the cat, the cat, cat,
right? So we have 7 out of 7, so 100%. Right there, you can start to see this isn't a good measure. Now let's look at the bigrams. So the cat, and the cat all appear in that first reference sentence there. So, but the cat, and cat, the doesn't appear anywhere. So this way we have 3 out of 6. So 50%. Again, this isn't a great candidate sentence. So neither of these scores seem to be a good measure. All right. So now let's look at the, go back up, the modified n-gram precision. So this is very similar, except to avoid a candidate sentence with just a single word or two words repeating, scoring highly, it's going to clip the maximum number of times a word can be counted or an n-gram can be counted towards the score based on the reference sentences. So let's look at unigrams. So we still have 7 unigrams in the candidate sentence, right? So there's 7 here. But now when we count how many times it appears in the references, we are limited to the maximum number of times it appears in the reference sentence. So the appears twice, right? It appears twice in reference 1 and once in reference 2. So we can count at most 2 thes. And cat only appears once in both reference sentences, so we can only count it once. So this way we have a total of 3, and we're going to divide that by the total number of n-grams. So in this case, we're doing unigrams, so that's a 7. So this way we have 3 out of 7, which is a heck of a lot closer to a good score than our 7 out of 7 for the unigrams on with just the precision. Now let's take a look at bigrams. So with bigrams, we still have 6. We still have 6 n-grams in the candidate sentence. But let's see. So how many of these n-grams appear in other sentences? So we see the cat. Yep, that's good. But I don't see the cat anywhere else. So that is going to be clipped to just 1. So we can only have 1, the cat. And then we don't have any other n-grams appearing anywhere else in these reference sentences. So now that means we have a total of 1 out of 6 bigrams. So that is a much more accurate score for this terrible, terrible candidate sentence. So now that we have our modified n-gram precision, let's look at calculating the rest. When candidate sentences are too short, they can score artificially high. So we want to add a brevity penalty to any candidate sentence that has less word than its best match length. Since our candidate sentence is not shorter than the closest matching length reference sentence, there is no brevity penalty. Finally, we want to calculate the blue score by taking the geometric mean of the test corpus's modified precision score up to length n. So in this case, we're using 1, and for n is equal to 1 for the unigrams, and n is equal to 2 for the bigrams, and positive weights, and multiplying it exponentially by the exponential brevity points. So we can see here that we have our calculated unigram blue score here. Now, when we do unigrams, it's not going to reflect as good as if we were doing higher counts, but we can start to see that a little bit here with the bigram. So now we've jumped down from 0.42 down to 0.26. So that's good. Now let's take a look at the event-to-event experiment setup. The authors of this paper set up 11 experiments with different formats of event representation. So at 0 here, we just have a baseline where the original format is tested. Then at 1, we have the basic format with the original words. Then at 2, where we're placing the people's names with the char notation. In 3, they fully generalized with named entity recognition for the named nouns and use WordNet and VerbNet to generalize the nouns and verbs. Okay, at 4, it's still generalized, and they continue to use they use continued chars so that the char numbers would persist for input and output. In 5 here, they added genres to the generalized format. In 6, they used a generalized event bigram. So that means they inputted 2 events in the same sequence and received 2 events in the output sequence. So in number 7 here, they continued to use generalized event bigrams, but this time with continuing char numbers. And then in number 8, they continue to use generalized event bigrams, but this time with genre numbers, right? And then in at number 9, they allowed multiple events to be extracted as single sentences. So they ensured they inputted those events in the same order that they were extracted. So here we see John and Mary went to the store, and we've got 2 different events there. And then in number 10, they continue to allow multiple events to be extracted as single sentences, but at this time they tried inputting them all. They tried inputting them in all possible orders. And then finally, in number 11, they continue to allow multiple events to be extracted as single sentences, but this time they inputted all of the multiple events into the network as a single n-gram. So they just put them all in as a single n-gram and then expected a result. So now let's actually look at those results. Remember that we want a low perplexity score, meaning that our model is performing well, and a high blue score, meaning that our language has been seen before in the test data. So we can see that the original words events had similar perplexity to the original sentence, right? So very, very similar. But the perplexity improved significantly once the character names were replaced with char tags, and even more so when the events were generalized. That one's kind of the one that won that for perplexity there. And then bigram. So now when we went into bigrams here, that improved the perplexity score even further, although not as much as just adding that genre information. So look at that generalized genre. And then down at the bottom here, we can see when we did the generalized multiple all to all, we got that best the best perplexity score though. So the blue score is fairly low for all experiments, with the highest score being with the original word. So right here, that's the highest score. Remember, we want the highest one. Now, the authors of this paper do not believe that the blue score is an appropriate measure for the event-to-event model because it emphasized the recreation of the input. So the next part of the system that we're going to talk about is the event-to-sentence network. The problem is that the event representation outputs from event to event are actually not human readable. Like that's what it looks like. So therefore, the output must be translated to natural English, something kind of like that. I don't know how natural that is, but it's kind of close. Since the conversion from a sentence to an event representation is a lossy procedure, as you can see here, so that's the input, and then that's the extracted event. We see we lose a lot of information. And the event-to-event network will not necessarily produce events that has already been in the training corpus. It's actually a non-trivial task. It's actually quite difficult. But the event-to-sentence network is a sequence-to-sequence model, just like the event-to-event system, except this time the aim of the model is to translate from an event representation into natural language English. So this model is trained on the story corpus and their corresponding events to learn how to reverse that lossy creation process. So the event-to-sentence experimental setup was nearly identical, except that it used beam search rather than a greedy algorithm to find the optimal solution while decoding. The beam search decoder works by allowing a number of multiple alternatives for each step. So this is known as beam width here. And at each step, the beam selects B tokens to expand the current partial search. This continues until the end of sentence is reached and the path with the highest probability is chosen. In my example here at the bottom, I have a simple beam search with a beam width of 2. John and Mary have the highest probabilities, and so their branch both expanded. And then the next two highest probabilities are taken, so John yelled and Mary moved. This type of beam width expansion continues until the end of sentence is reached. So with the experimental setup for event-to-sentence, so the first 3 experiments consisted of testing the 3 categories of the event-to-event experiment. So we have original word events. So here we're just looking at the original word. We're not changing anything. Generalized events. So that's where we're just using char, one, escape, location, and then all generalized events. So this one is where we're passing in multiple or a single sentence and getting multiple events out of it. So alternatively, they also split and prune sentences, so S and P, removing prepositional phrases, splitting phrases on conjunctions, and when the sentence does not start with a pronoun, removing the first words. So what happens is Lenny begins to walk away, but Sam insults him, so he turns and fires, but the gun explodes in his hand, so that's why one sentence becomes Lenny begins to walk away. Sam insults him, he turns and fires. The gun explodes. So the results of the event to sentence experiment show that while generalizing events improve perplexity quite a bit, keeping the original words while splitting and pruning produces the absolute best BLUE score. And unlike with the event-to-event experiments, the authors believe that the BLUE score is the more appropriate metric for these experiments because it is a translation task. The event-to-event and event-to-sentence model work together to produce fully autonomous open story generation. The sentences are parsed and translated into event representations, and those events are fed into the event-to-event model to generate the next events in the sequence. To ensure they're readable, the generated events are passed to the events-to-sentence model to translate them into natural language. So that's happening here. The generated events are also passed back to the events-to-events model to continue with story generation. That's happening right there. Let's take a look at some end-to-end generation and translation. So let's take a look here. Looking at these generations, we can see the difference, the different event representations and how that they make it down out to the final output of the models. It looks to me like the generalizations tend to make kind of more robust story events, while the original words, while they do seem a little shorter, they seem a little easier to read. The authors of this paper actually have some future plans, and what they plan to do is they plan to implement some working memory to retain the names and nouns that are removed during the event generalization so they can be added back during the event-to-sentence translation, which could improve the output greatly. While there still is a lot of research to be done in the area of open story generation, the authors of this paper have created a working model that generates relatively coherent stories.